You ever stop and wonder what's actually happening behind the walls when you flip a light switch? I mean, that instant, reliable power. It feels so simple, right? But it's actually the end result of this incredibly complex design process. It's a whole hidden science of critical calculations and safety checks, all designed to keep us safe every single day.
So, what is that science? How do we guarantee that the immense power of electricity gets delivered reliably and, way more importantly, safety to every single socket we use? Well, the answer is tucked away inside a super strict set of engineering principles we call the wiring rules. And really, it all boils down to this one core principle, stated right here in the Australian and New Zealand wiring rules. This isn't about convenience or efficiency first. Nope, it's about one thing, above all else, protecting life and property. That is the mission.
So, to get that level of safety, every single electrical installation doesn't start with wires and circuits. It actually starts its life as an idea, a blueprint that's built on a foundation of really critical questions and some very careful planning.
This five-stage process you see here, this is the roadmap for pretty much every safe electrical system, and it's going to be our roadmap for this explainer. So let's start right at the beginning with the brief and the planning phase.
So, stage one, the brief, is basically pure detective work. A designer has to know exactly how a facility is going to be used. I mean, is it a small home office or a massive industrial plant? They need to understand the electrical load. Is power going to be drawn constantly, or is it cyclical? You know, like big machinery that's starting and stopping all day. Getting these answers right is absolutely crucial to figure out the maximum demand and shape the entire blueprint. Okay, so once the brief is crystal clear, we move into planning. This is where we start to look into the future, using all that information to estimate the absolute peak amount of electricity the system will ever need to handle. But it's also where we have to start dealing with the fundamental physics of electricity.
And here's a really key concept, voltage drop. The easiest way to think about it is like water pressure in a really long garden hose, right? It's super strong right at the tap, but by the time it gets to the other end, it's a lot weaker. Well, electricity does the same thing. Voltage, which you can think of as electrical pressure, decreases the farther it travels down a wire. A good design has to calculate this and manage it to make sure the thing you plug in at the very end of the line gets the power it actually needs to work safely.
All right, with a solid plan in place, we get to the real heart of the process, the design phase. This is where all those abstract numbers and plans get turned into a precise, calculated blueprint where safety is engineered into every single part.
Let's go back to our roadmap. We've got the brief and planning sorted. Now we are in the critical design stage, and this, folks, is where the most important safety calculations happen.
First up, we have to calculate the fault level. This is the absolute maximum, worst-case scenario surge of current that could ever happen in a short circuit. Imagine you're building a dam. You don't build it to hold back the river on an average Tuesday, right? You build it strong enough to survive a catastrophic, once-in-a-100-year flood. That's the fault level. It makes sure the system is tough enough to survive the absolute worst without, blowing up.
But you also have to protect against the smaller problems, and that is where fault loop impedance comes in. This calculation makes sure that even the tiniest dangerous fault is still strong enough to be detected. So if the dam is about surviving a flood, this is like making sure your smoke alarm is sensitive enough to go off at the very first wisp of smoke, not just when the whole room is on fire. It guarantees that the safety devices trip instantly when you need them most.
And this just perfectly illustrates the two sides of the safety coin, doesn't it? The system has to be strong enough to withstand the maximum possible fault, but it also has to be sensitive enough to react to the minimum possible fault. Both of these calculations are absolutely essential for a safe design. One is about survival, the other is about protection.
So how fast does that protection need to be? Well, for a standard power outlet, the rules say the maximum disconnection time is 0.4 seconds. That is literally faster than you can blink. If a dangerous fault happens, the power gets cut before your body can even really register the shock. That tiny fraction of a second is the difference between a scary moment and a real tragedy. So with all that in mind, how is the right wire actually chosen? Well, it's a really careful balancing act. The cable has to be thick enough to survive that massive fault level we talked about, but it also has to carry the normal load without getting hot. Then it has to be big enough to manage voltage drop over its entire length, and it has to be perfectly matched to the safety device that's protecting it. It's a four-step check for every single circuit. Okay, so once this incredibly meticulous design is complete and it's all verified on paper, it's finally time to move from the digital world into the physical one. It's time to turn the plan into actual power. Our roadmap leads us to the next big stage, installation. This is where the blueprints become reality. Cables get run, switchboards are connected, and outlets get fitted into the walls.
And here is a rule that is absolutely non-negotiable. The installation has to perfectly match the design. Exactly. You can't just sub in a different cable because it's what you've got handy. A slightly longer cable run or a different type of circuit breaker can throw off all those critical safety calculations, forcing a complete redesign. The entire safety of the system depends on this precision.
So the system's built, the wires are in the walls, but we are not done yet. Before any real power flows through that system, the whole thing has to go through one final, crucial series of tests to prove it's safe.
And that brings us to the final stage of our journey, verification. This is the moment of truth, where we prove that the system isn't just built, it's built safely.
Verification is a two-part deal. First, there's a visual inspection, just to confirm that what was physically built is an exact match for the design documents. Then comes what's called determinative testing, where special instruments are used to measure the actual electrical properties of the circuits. This confirms that the real-world performance matches all those theoretical calculations from the design. It's the final proof.
So you see, the safe, reliable electricity we use every single moment of every day, that doesn't just happen by accident. It's the product of this invisible, meticulous, and legally required design process, a hidden layer of engineering and physics that's dedicated entirely to keeping us safe.
So, the next time you plug in your phone or turn on a lamp, maybe you'll think of that journey, from that first question to the final test. This whole invisible network of calculations, all working in less than the blink of an eye, just to keep you safe.